There it is. Oh, no, those are baby goats. There we go. Let's go to this first, and then we'll go back and look at carbon dioxide. So you were supposed to do the last 4 on this set, and so you can just, can you guys, this is a good question, can you guys see your work if you've submitted it? Can you look at it? Anybody? Are you able to look at it?
Yeah, we can.
Okay, cool. So just maybe open up your drawing or just copy down what I do on a piece of paper. Okay, so we've already done these. So I look at this H2S. Remember, this is really a subscript. H2S is a sulfur with 2 hydrogens attached. And remember, if there's a single element, a symbol without a subscript, usually you want to start with that one first. Okay, so sulfur. And then I have to figure out what the valence electrons are for sulfur. Normally I'd be calling on people and asking you, but it's really hard to go back and forth between my presentation and your responses. So hopefully you guys know sulfur's in the same family as oxygen. It has 1, 2, 3, 4, 5, 6 valence electrons. It makes 0 difference where you put the lone pairs and the unpaired ones. Okay, I just happen to do it this way. You can do it however you like, but there should be 2 lone pairs and 2 unpaired electrons. One thing though, I do want to emphasize, those lone pairs should be next to each other. This will not make a linear molecule, just like water is not a linear molecule. And you don't know about shapes yet, but you obviously hopefully know what a line is. Okay, so these lone pairs should be side by side. Okay, now we have to put in hydrogens, and of course hydrogens have 1 dot, and I know I told you guys to do the dot diagrams for each one, so you should have had 6, 1 times 6 and 2 times 1. And so there should be 8 valence electrons, and there are. And the other item that I asked you to do on these was to circle the, excuse me, the way that they either get an octet or a duet. And again, for hydrogen, the best it can do is take its 1 electron and borrow 1 from sulfur, so hydrogen gets 2. And then sulfur has 6 and 1 from each of the hydrogens to get its octet. So this is going to have the exact same shape as a water molecule. Oh, lovely. My cat just brought in a gopher. At least it's dead, I think. Oh my gosh, it'll be so nice to be back in the classroom. Yeah. Sorry, get my composure back here. Usually he just brings them in and eats them at our by our shower downstairs, but he wanted to show off. It's the joy of having a cat door. They can bring in things. Yay. What was I saying? I was saying that this is the same shape as a water molecule. That's what I was saying. Okay. And we'll learn more about that in coming days. Any questions about this molecule? All right, I'm going to move on. And so the next one is phosphorus with 3 fluorines. So phosphorus has 5 valence electrons. It has 1 lone pair. And again, it doesn't matter where this lone pair is. You can put it on the side, on the bottom. I typically put it on the top, at least to start. Doesn't matter. And then 3 fluorines. Fluorine's a halogen. 1, 2, 3, 4, 5, 6, 7. So we're going to have 1 times 5 and 3 times 7. Oops, I did that backwards, but you guys get the idea. Okay, so when I'm all done, oh, I didn't count these. Did I count these? 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. And 5 and 21 makes 26 dots when we're all done, hopefully. Put the singleton in the middle. And then put the other ones around it. And like I said, halogens are tedious because they have so many valence electrons, but they only bond one time. So, unfortunately, this goes kind of fast. If you have a marker, it goes fast. If you get a pencil, it goes slow. So 7 and 1 is 8, 7 and 1 is 8, 7 and 1 is 8. That's 24 plus 2 more are 26. And then the last thing is to find the octets. 7 and 1. 7 and 1. Oof. 7 and 1. And then 5 and 1, 2, 3. And the octet rule is satisfied. Questions about phosphorus with 3 fluorines? Please. I don't know what I'm doing. Okay. Everybody good so far? Hopefully. So the next one is nitrogen with 3 iodines, and that is going to have the exact same appearance, different symbols, but nitrogen and phosphorus are in the same family, fluorine and iodine are in the same family, and we have the same number of them, of course. So this is going to look absolutely identical. This is going to be nitrogen with 3 iodines. This could also be, I'm just going to say this could also just as easily be nitrogen with 3 hydrogens. Okay, they would not go to the iodines. I'm just putting that on there to show you. Because again, nitrogen can bond 3 times because it has 3 unpaired electrons. Okay, so that again is ammonia. It looks like it's a T shape. It is not a T shape. I actually have this little gizmo. I saw this at Staples years ago and said, oh my gosh, that's an ammonia molecule. It's actually a massager, but the blue top, blue is the typical color in molecular model kits for nitrogen because it's what makes our atmosphere blue. The light reflecting off of those molecules. Anyway, and then it has 3 little legs, and they're pushed out of the flat plane. And this is close to the shape of the ammonia molecule. Anyhow, just FYI, it's not a T. This lone pair pushes them down. Also with iodine, same with phosphorus and fluorine. So again, I should erase those. The hydrogen is just there to just put that in there to demonstrate ammonia for you. And again, we have the lone pair. So it is going to have, sorry, I don't know what I'm doing here. Iodine has 8. This iodine will have 8. This iodine will have 8 when they're bonded to nitrogen. And then the 5 on nitrogen plus 1 from each of the 3 iodines gives nitrogen 8 as well. Questions on that? All right, we're going to do lots of bonding with carbon. Remember, carbon is in group 4A or 14, and then it has 4 valence electrons. It can bond multiple times. Carbon's crazy. And like I said, do just a little bit of organic chemistry introducing hydrocarbons in a few weeks. So each of these electrons needs a buddy. Along comes fluorine. Again, fluorine is a noble gas. It has 1, 2, 3, 4, 5, 6, 7 valence electrons. So those fluorines are going to come in here. And this is going to have the same shape as a methane molecule. So I had the space filling model shape on my PowerPoint on Tuesday. On paper, this looks like a flat plus sign. It is not. Okay? And you've got to remember everything's in three-dimensional space, which is kind of weird, I know. So again, I'm going to make these different colors. So carbon has its 4, each fluorine has 7. By borrowing one from carbon, each fluorine will get its octet. By borrowing one from each of the fluorines, or sharing one, they're not really taking one, the carbon atom will get its octet as well. And everybody's a happy camper. Questions on any of those? Guys get them all correct? Everybody good? Questions? No questions? What do we got there? Yes, yes, yes. Okay, cool. So everybody's okay with those first ones? I'm going to move on to the, I can't remember what I assigned to you guys. Did I assign the first ones or the last ones? Oh, I know, I didn't do ammonia and water. Is that right? Yeah, I just had to do the first 4. Okay, sorry, I have to remind myself. So in set number 2, there's carbon, and some people were confused about this. So carbon, again, is going to have 4 valence electrons. Each of the hydrogens only has 1. And then each of the iodines is going to have 7. So the atom that has no subscript, now that's going to get confusing here, but there's only one option. But the atoms without subscripts are usually the ones that are going to go in the center. And always, if it's carbon, you should probably put that one in the center. So that honk rule, there's 1 bond, 2 bonds, 3 bonds, 4 bonds. The one that bonds the most should go in the center. Okay? So for sure it's carbon. You've got 1 of these, 2 of these, and 2 of these. So 2 times 7, 2 times 1, and 1. 4. There we go. I knew that was wrong. So 4 and 2 and 14 should be 20. Okay, so here's carbon, again in the middle. And it really doesn't matter where you put the hydrogens. You can put them side by side. You can put them on opposite sides. It's irrelevant. I'm just going to put them here for yucks. And then iodine will go on the other 2. So don't get yourself tied up in a bunch trying to decide where they go. It really does not matter. Okay? What matters is that you get the right number of dots. So again, here we are with carbon bonding to 4 things, 2 of them hydrogen and 2 of them iodine. They could be all different things. They could be all the same, like methane. So hydrogen gets its duet, iodine gets its octet, and carbon also gets its octet. Hydrogen fluoride can get simpler. Hydrogen has 1, fluorine has 7. 8 total. Again, you can put the dots side by side, or you can put them up and down. Again, it doesn't matter. Hopefully that was straightforward. Phosphorus with 3 chlorines is going to look just the same as phosphorus with 3 fluorines. Okay? Same central atom, same family for the second element. Fluorine, chlorine, bromine, and iodine, all halogens, all have 7 valence electrons. And then methane, super simple also. So forgive me, I'm just going to draw this really fast. Kind of cheating there. because I know where we're going with it. Hopefully you do too at this point. If you don't, it's okay. So phosphorus has 5 of its own, including this lone pair. 3, 1 from each of the chlorines. Each chlorine has 7 plus 1 from phosphorus. Methane, again, 1, 2, 3, 4 hydrogens, 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 hydrogens. Carbon gets its octet, each hydrogen gets its duet. Good so far. I did ammonia for you already. Water looks just like the sulfur with 2 hydrogens, except it is oxygen with 2 hydrogens. I just switched up the dots so I didn't switch pen color. Duet, duet, octet. You didn't have to do those, so don't freak out. And then this last one is, I do want to do this one for you, so I'm going to get rid of this mess. This last one is multiple carbons together. Okay, so I've been telling you that you should put the one without without a subscript in the middle, but using this should always start with the one that has the most available bonding. So hydrogen can only bond once, oxygen can only bond twice, nitrogen normally only bonds 3 times, always, actually for nitrogen it's always 3, and then carbon's always 4. Okay, so since I've got carbon, hydrogen, and fluorine, these guys only bond once. I have nothing else to put in the middle except carbon. So let's start with carbons. So this would be a bond, of course. And then there's 4 hydrogens and 2 fluorines. It honestly doesn't matter where you put those, but typically they're going to try and go for something symmetrical. So I'm going to go ahead and put the fluorines. Oh, I lied. I'm going to put the hydrogens in there. I don't know why I said fluorine and then the hydrogen. Goodness gracious. Okay, so put 2 here, and then put 2 fluorines on each carbon. So whenever you have something that's kind of even, like these are, go ahead and spread them out evenly. So I'm going to magenta, see what that looks like. So not much different from red, I guess a little bit. We're going to talk about the fact that these bonds actually rotate, but again, that's coming attraction. So make it kind of symmetrical, make it look like mirror image on either side, whatever. Again, hydrogen, hydrogen, fluorine gets its 8, duet, duet. And then how does carbon get satisfied? 1, 2, 3, 4. So each carbon gets an octet part of the time. Okay, that's really sloppy, but hopefully that works for you. We did oxygen and, on Tuesday, I believe. Oxygen that you breathe. Remember, these share a pair of electrons. So there's a double bond between the oxygens. So it's got 6 of its own. Here, let me change the colors to make it more obvious. I don't know if that helps you guys or not, but it helps me. So each oxygen has 6 electrons of its own, and then it shares 2 with the other oxygen. And then we can also draw a double bond like this. Carbon dioxide is similar. I'm just going to do it right now, and then I'll go through my slides. Again, carbon has 4. Each oxygen has 6. And when you try to be sure that the unpaired electrons are taken care of, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 4. So obviously there's a bond here, I hope you can see. sharing between two atoms. And then these unpaired electrons come together to make that secondary bond. Okay. And you have to understand that just because you draw them on your paper in a different place doesn't mean they can't. So carbon dioxide is a linear molecule, and it is double bonded. So how does that satisfy the octet for each of them? I hope you can see it does. This central carbon has 4 electrons of its own. It borrows 2 from each of the oxygens. So part of the time it has an octet. And then the oxygens have 6, and they borrow 2 from the carbon to get their octet. So you're going to want to have an eraser around, or just make a second drawing if you figure out that you're doing it in pen and you have to move electrons. You can cross them off. And we'll come back to that later. So, where's carbon dioxide? There it is. Sorry, are questions at this moment? Anybody? Probably not sure what to ask. All right, so you know CO2 can be compressed into dry ice. We've talked about that before. That's what dry ice is. It's not ice at all. It's not water frozen. It is solid frozen carbon dioxide, which is normally a gas at room temperature. When you put carbon dioxide into sodas for the fizz, some people like it, some people don't. It can be highly explosive if you shake up your soda cans. But it is a gas, and when you open your can, you're opening sodas and any carbonated beverage is usually packaged at about 2 atmospheres of pressure. So they can shove those gas molecules into the liquid, and then when you open it to regular atmospheric pressure, especially up here where we have a little bit lower pressure than normal, than the valley, for example, it comes out, okay, and it will bring the liquid with it often, as I'm sure some of you have experienced. So again, carbon has 4 unpaired electrons, and it will form a double bond. And there's still these lone pairs out here, and notice how they've shifted them sideways. Rather, if you have them at 12 o'clock and 3 o'clock, that's fine, or 12 o'clock and 9 o'clock. Totally fine, like this bottom drawing, doesn't matter to me, okay? But there are 4 electrons total, 2 pairs, so that makes a double bond. And in molecular models, carbon is usually black, like charcoal, and oxygen is red. Side, which not that important. All right, topic of the day, coordinate covalent bonds. How are they different? Well, it turns out, remember, carbon goes with 2 oxygens, but it can also go with 1, and we've talked about carbon monoxide earlier. What's going on here, our best explanation of what's going on here, why this bond would happen, is something called, well, it gets a double bond, but it's not a double bond in the normal sense of the word. So in this molecule, what ends up happening is the oxygen borrows 2 of the carbons. That's not surprising, but the carbon, in order to get an octet, has to move. Sorry. Oxygen actually, moves 2 of its lone pair molecules. So this molecule ends up with something closer to a triple bond. And that is a very difficult bond to break, which is one of the reasons why it's very difficult to clear carbon monoxide from your bloodstream. So by doing this, carbon is able to have its octet, and oxygen also has an octet. So a coordinate covalent bond happens when both electrons in the bond come from 1 atom. And another technique that's used to demonstrate that one of the atoms is donating both of the electrons is a little arrow. So oxygen is notorious for doing this, and oxygen provides, in this case, 4 of the electrons in this triple bond. Normally be 3 and 3, but in this case it's 4 and 2. Okay? And everybody gets their octet. And usually we're just going to show it as 3 lines instead of having the arrow, but some books use the arrows, just so you know. Did I have the definition? I think I had the definition on there. No. Oh, there we go. So according to covalent bond, both of the electrons in the shared pair are coming from the same atom. And it's a lone pair, and it's usually oxygen. So you might recall that most polyatomic ions have oxygen in them, and this one example isn't going to be it, but most of them do, and that's why they form nitrite and nitrate, sulfite and sulfate, these coordinate covalent bonds with the oxygens. But in this case, we're going to look at ammonium, and I've shown you this before, so hopefully this is just a review. Remember, ammonium's NH4 with a positive charge, and it has a coordinate covalent bond. That bond is coming from the lone pair on the nitrogen. Okay? Coordinate covalent bonds with oxygen are from a lone pair on the oxygen atom. Okay? So remember, nitrogen has 5 valence electrons, hydrogen have 1, should have 9 total. And remember, a positive charge indicates there's a missing electron. Remember that hydrogen, when it loses an electron, becomes a hydrogen ion. And so normally we get ammonia. However, that hydrogen ion is attracted to those lone pairs that are very sticky, and we form the ammonium polyatomic ion. It's a coordinate covalent bond because both of the electrons are coming from nitrogen. Hydrogen, the proton here, is not contributing. Again, you just draw it like a normal dot diagram. But when we do ions, drawings of ions, I don't have any on the homework, but when you do drawings of ions, the convention is to put square brackets around them and then put the charge on the outside of the bracket, okay, to indicate, in this case, that it lost an electron, has less electrons than protons. Most of them are going to have extra electrons because they're negative. This is a whole bunch of common compounds. You're welcome to peruse that in your textbook. Hydronium is the ion that forms in acids. And again, it's a hydrogen ion, the proton, attracted to a water molecule because oxygen has this lone pair that's sticky. It has 2 of them. And so oxygen is making that bond. And actually, since, when this hydrogen ion comes into the left-hand side of this oxygen, then both electrons in the bond are coming from the oxygen, which is why the arrow's in there. Again, square brackets to indicate it's an ion, and a charge to indicate whether it's gained or lost electrons. Boron is in group 3A or 13. It's at the top of aluminum. Each fluorine has 7 valence electrons, as you know. This, we didn't learn this ion, but just hang in there. Boron tetrafluoride with a -1 charge has 4 fluorines. We'll learn how to name them later. Notice that there's no space, no electron on the boron atom here. So from somewhere, from some other atom comes in an electron. And then that would give it, of course, a negative charge. And then the last thing that we would do would put those square brackets around it. So we want to make sure that boron has an octet. It does by sharing with, by sharing with the 4 fluorines. It's fine. So boron has 3 plus this 1 from outer space, and it ends up with, whoop, sorry, 8, so that was lame. And then each of the halogens have 7 and they gain 1 by sharing. All right. Questions? It's weird stuff, I know. Anybody with questions? No? All right, I'm going to go back to the problem set that has multiple bonds and do a couple of these and then leave you with some to do. There's no questions. Try and show you how to get some of these done, because we still have time. All right, carbon with 2 sulfurs. Again, carbon has 1, 2, 3, 4. Each sulfur is 1, 2, 3, 4, 5, 6. So we're going to have 1 times 4 and 2 times 6. Did it again. 12 and 4 is 16 dots total. So start with your carbon in the middle. And then go ahead and put the sulfurs. Just make it look balanced for right now. It's fine. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so we're off to a good start. We have a bond between carbon and sulfur on each side. However, hopefully it's really obvious that there are not 8 electrons around any of the atoms. Right? Sulfur's got 1, 2, 3, 4, 5, 6, 7. Both of them do, and then carbon's got 1, 2, 3, 4, 5, 6. So neither of them, I'm going to make these red, neither of them have an octet. So how can we fix that? Hopefully you're way ahead of me. These unpaired electrons need buddies. So this one's obvious because they're on the same side of the symbols, but this one does the same thing. Okay. They migrate, they're always moving around. They're the only stationary on your paper. Can't emphasize that enough. Okay. So these two and these two, it doesn't matter where you put them, top or bottom. I'm just going to put them on the bottom. And then we've got our octet satisfied. Prove it to yourself. Sulfur's got 1, 2, 3, 4, 5, 6, 7, 8 part of the time. Both of them do. Carbon's got 1, 2, 3, 4, 5, 6, 7, 8 part of the time. So what do we have? We have double bonds between the carbons and the sulfurs. Questions on that? Okay, let's try. Let's try 2 carbons with 2 iodines. Oh, excuse me, I lied, that's 4 iodines. So 2 carbons, we should have 2 times 4, and we should have 4 times 7. We should have 32 total. Oh, I didn't count these. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yep, we got 16. Okay, so we should have 32 total on this carbon. Again, 1, 2, 3, 4. Carbon, 1, 2, 3, 4. Each iodine has 7. Again, it doesn't matter, but just make it kind of symmetrical. So put 2 iodines on this carbon and 2 iodines on this carbon. Same here. I'm going to put on the bottom just because they'll try to spread out. So, one thing with double bonds, they do not rotate. They will be frozen in space, and we'll talk more about isomers. Sure. All right, so this looks okay. All the iodines are satisfied. They've got their octets, but when you count up electrons, 1, 2, 3, 4, 5, 6, 7 for carbon. 1, 2, 3, 4, 5, 6, and borrowing only 7. But hopefully you all see those unpaired electrons have to have a buddy. So we're going to move them in between the two atoms that they're coming from. Okay, so again, it doesn't matter whether we put them top or bottom, it's irrelevant. You know, a lot of people worry about that kind of stuff, it's not important. And once we do this, we end up with our double bond, 2 electrons, one coming from each carbon. We already know that the iodines are satisfied, but now let's just double check the carbons. 1, 2, 3, 4, 5, 6, 7, 8. Yes, that's an octet. 1, 2, 3, 4, 5, 6, 7, 8. Also has an octet. Okay. All right, I'm going to cut it here. I'm going to ask you to do these last 4. I will stick around if there are any questions, because there probably are. And I will post this video as soon as I can today. Where are you guys? There you are. Any thing I can answer for anybody right now? Do you want us to resubmit a question? No, Amber, it's not necessary. Thank you for asking that.